Hi, and welcome to 7.1 Tangential Velocity. In this lesson, students will be able to calculate the tangential velocity and describe the motion of an object undergoing uniform circular motion. So we are starting Unit 7, Circular Motion. The do now that we did in class is similar to this. It says the velocity of an object points tangent to its circular path. So we already discussed how if you're moving clockwise like this, your tangential velocity points tangent to the circle. Okay. And it changes, right? As you go around the circle, the velocity, uh, changes direction. So far in this class, we have studied motion, linear motion and parabolic motion. And we've also discussed forces by discussing Newton's laws, friction, and gravity. And we will use what we have learned to study the motion of objects moving in a different type of path. So not linear, not a straight line, and not projectiles, but this different type of path. Uniform circular motion. Why is it uniform? It's an object that moves in a circular path at a constant speed. So the fact that it's a constant speed makes it a uniform circular motion. Critical thinking. So when an object is moving in uniform circular motion, or UCM for the fancy people, is its velocity constant? Why or why not? We're saying, so think about it. Pause the video, think about it. Is the velocity constant? Well, it says it has to be a constant speed. For uniform circular motion, the speed has to be constant. But since the velocity changes its direction as you move around the circle, that means the velocity is not constant. The velocity changes. Why? Is velocity a scalar or a vector? Remember, velocity is a vector, VV, and speed is a scalar, SS. The direction doesn't matter for the speed, but the direction does matter for the velocity. So as you move around the circle, since your direction changes, your vector, your velocity vector changes. So you have a changing velocity even though it's a constant speed, constant magnitude, changing direction. Okay. So let's get an equation for this tangential velocity. We already know the equation for the velocity. What is it? V is equal to, what do you think? D over T. Okay, and we're talking about an object moving around in a circle. And what is the distance around a circle? What is the distance around a circle? That's the circumference. So if you take the time it takes for one circle and the distance that you traveled along that circle, you could find your velocity. So do you remember the circumference equation? What is the equation for circumference? C is equal to, what is it? 2 pi r, or you might have said pi times the diameter. All right, remember, the diameter is equal to 2 radiuses. Okay, so that's why 2 pi r, that's the one that we like to use because we like to use the radius. Cool. And then we got the T, and then I have a subscript here. T, one circle. Does that look like a nice subscript to be writing every single time we talk about circles? No, I don't think so. Let's come up with a better terminology for the time it takes for one circle. It should be like a special thing, the time for one circle. It is a special thing. It's called the period, and we use a capital T instead of the lowercase t for time. We're just using a capital T because it's a special type of time. It's the period of time or the amount of time required for one complete rotation. The definition is right in the word there. It's like I said, the period of time required for one complete rotation. How much time does it take for one circle? All right, so here's an example. It says if it takes 30 seconds to run in a circle 5 times, how long does it take to run in a circle 1 time? In other words, what is the period? So pause the video here, think about it. You probably already know how to do this. So in your head, did you go, okay, well, I have 30 seconds, and if I divide that by the 5 cycles, then that must mean it takes 6 seconds per one circle or cycle. Okay, so this is kind of a formula in and of itself. You took the time and you divided it by the total number of circles. So let's make that a formal formula or an equation. T, capital T, the period, is equal to the total time that they give you. In this case, it was 30 seconds, divided by the number of revolutions that it takes for that whole time. So sometimes they'll tell you like this, and sometimes they'll just be like, hey, it takes 30 seconds for one cycle. And then you don't have to do this. If they say it takes 30 seconds for one, then you already know the period. It's 30 seconds. But sometimes you'll have to calculate it, so this is a handy formula that we can use. So this is it, 2 pi r over the period, their circumference divided by the period. So, and the v is the tangential velocity. If you wanted to separate it out, you could make it vt for tangential, but that gets a little confusing because like there's a t here and everything. Just remember, it really is just the same equation, the distance divided by the time. It's the distance, the circumference, divided by the period, the time for one circumference. Okay, so I think we get that. So where is this nice new, is it a new equation? Well, where is it on the reference table? Try to find it if you can. You might think it should be on the back page, and I agree, it would be nice if it was on the back page, but guess what? It's not on the back page. Why? Because they already told you this. So the people who made this reference table wanted to say, look how many equations there are. They can't put every single one. So it's up to you. You can either write it over here, well, that's just 2 pi r over the period. Or actually, this is where the other circular motion stuff is that we're going to learn in this unit, Unit 7, circular motion. So if you want, you could write in, just to be specific, 2 pi r over the period, okay? And if you really wanted to, you could also write the period is equal to the time divided by the number of revolutions, which we, talked about in the previous slide. So I highly recommend writing that in if you can. So a quick concept review and then 2 example problems. It says, where should the thrower release the hammer? This is an Olympic hammer thrower. Have you ever seen a hammer throw before? It's really cool. They whip around in a circle to get a lot of speed on that hammer, and then they release it and they try to throw it in this area here. There's a net all around to make sure everybody stays safe. So where should they throw it if they want to go in like this direction here? Where should they release it? So over here I have the diagram. They're moving around in a circle this way, and they want the hammer to go this way. So where should they release it? Pause the video and think about it. Some people say, well, they should release it right here because that's closest to the desired motion. But if they released it right here, remember it says hint, what is the key word used earlier to describe the velocity? The direction of the velocity is tangent to the circle. So if they did release it here, the velocity at that position is pointing this way. So that hammer would continue to move in this direction instead of this direction, and whoever's standing over here, hopefully nobody, would get a hammer in their face, which is not fun. So if you wanted to go this way and you're rotating this way, then where should you release it? At point C. At point C, the velocity vector looks like that. So if you release the tension in the rope there, it's just going to continue in its state of motion. Actually, because the hammer has inertia, right? It's just going to continue in a straight line. Obviously, gravity will pull it towards the ground, but you don't have the, and we'll talk about the centripetal force in the next video. All right, so point C. I think you probably got that. Let's do an example. It says a toy train travels around a circular track once every 10 seconds. If the track has a radius of 1 meter, what is the speed of the train? Feel free to pause the video, write down some givens in the unknown, and see if you can figure out what the speed of the train is. Okay, so hopefully you paused the video and thought about it. It says it goes once every 10 seconds. So not only is that telling you the time, it's telling you the special type of time. It's once time every 10 seconds. So that's the period. And the track has a radius of 1 meter. Okay? It says, what is the speed of the train? So the speed or the tangential velocity is what we're looking for. So you could do v is equal to 2 pi r over the period. The velocity is equal to 2 pi times 1 divided by 10. So the velocity is equal to 0.628, well, so we'll just call it 0.6 meters per second. Okay, 0.6 meters per second. If you said, oh, I want to do mental math and it's pi over 5, Mr. Nangle, because 2 times 1 is 2, 2 divided by 10 is 5. You know, technically you're not wrong, but just break out the calculator, because how many times have you been riding in the car and be like, oh, wow, I'm going pi over 5 miles per hour? Like, we don't use pi in that instance. You just do the math, okay? Cool. All right, example number 2, it says, in an experiment, a 1 kilogram rubber stopper is attached to one end of a string. A student whirls the stopper overhead in a horizontal circle with a radius of 0.75 meters. The stopper completes 12 revolutions in 6 seconds. What is the speed of the rubber stopper? It seems like a weird thing to be doing, right? But this is actually a classic physics lab where you can calculate the not only the tangential velocity, but we'll talk about the centripetal acceleration and the centripetal force that acts along the string. I remember doing this lab, and hopefully you get a chance to do it in the classroom. All right, so this is moving in a circular path. I'm trying to draw it specifically so that we could see that this is 0.75 meters. This is the radius. All right, so part of the experiment is measuring how long this string is. So you could find the radius experimentally. You know what the mass of the object is, and that'll help find the force. But right now we're just looking for the speed. So let's do some calculations. All right, so you could say like the n, the number of revolutions, if you want, is equal to 12 revolutions. And it says the time for that is 6 seconds, and the radius is 0.75 meters. Yeah, they tell you the mass. That's going to come in when we do, because F equals ma, right? So F is going to be the centripetal force. But for now, we don't really need it. Okay. Um, cool. So we need to know what the period is, because we want to do like, okay, it's moving in a circle, so that's 2 pi r, but we don't know the time for one circle. We need to figure out what the time for one circle is, the period. So we'll start by going, the period is equal to the time divided by the number. We wrote it like this, number of revolutions. Okay, if you want, you could write it like this. I didn't want to introduce too many variables, but n is just like the number, the amount. You've seen that in chemistry, the amount. So the period is equal to the time, 6 seconds, divided by the amount, 12 revolutions. So you do the period, and you get 0.5. See how the units, it's a second divided by a revolution. So, right, this is seconds, 0.5 seconds per revolution, which is what we want. It's the definition of the period, how many seconds for one revolution. So yeah, the units are good like that. And hopefully you didn't do 12 divided by 6. That's a trick people try to fall into, because they just do the mental math quick in their head, and they do 12 divided by 6 is 2. So that's a trick. Remember, it's the seconds divided by the revolutions. All right, and now we're ready to do V is equal to 2 pi r over the period. The 2 pi times the radius, 0.75, over the period is 0.5 seconds. Okay, and pi, we know pi is 3.14, but just in case, 3.14, or you could just use the pi button in your calculator. And you get 9.4 meters per second. Okay, that is the speed. So it says, what is the speed? Oh, Mr. Nangle, you're calculating the velocity. Remember, the speed is just the magnitude of the velocity. Okay, technically, if it looks like it's going this way, from overhead, what would you call that direction? Maybe what is that? Counterclockwise. So if you wanted to specify a direction, you could write the direction and be like, ooh, that's the velocity because it's the magnitude and the direction. But most of the time, they're not going to want that when they ask for the tangential velocity. The speed or the magnitude of the velocity is fine. Okay. All right, one more critical thinking question. And this one's a doozy, so really get your critical thinking cap on. Okay? This is a record for any of you who don't know, and it spins around in a circle. All right, and this is how they used to play music. It says, where should the toy be placed so that it has the greatest circumference? Should this little toy be placed on the green, yellow, or red dot so it has the greatest circumference? Pause the video and think about it. Did you say the green dot? I hope so because 2 pi r, right? 2 pi r, we want the largest radius to get the greatest circumference. Okay, that wasn't too bad. Well, how about this one? Critical thinking cap should be on. Where should the toy be placed so that it has the greatest period? Pause the video and think about it. Which would give you the greatest period? Okay, hopefully you had time to think about it. Well, I'm going to do a little animation here. Let's rotate the record player and let's see what happens to those points. They all stay in line with each other and they all stopped at the same exact time. They actually all have the same period because the disk is a rigid object. The record is a rigid object. So it makes sense that they all have the same period because if they didn't, then it would be like a whirlpool effect where one's moving faster than the other, but they should all be in a straight line. So all the points stay in a straight line as you go around a circle, and it completes a circle in the same amount of time. So they all have the same period. Okay, so the green has the greatest circumference, but they all have the same period. Where should the toy be placed so it has the greatest velocity? This is the true question. Pause the video and think about it. Let's see that animation one more time and look closely at the one that you think has the greatest velocity. And this isn't a trick. All right, they're going to have different velocities. Which one has the greatest velocity? Look how slow red is moving compared to green. Green was moving all so fast because it had to move in the greatest displacement. Green had the greatest displacement, the greatest circumference, and they all had the same amount of time. So since I'll go like this, green had the greatest displacement, and this is a direct relationship. So this is the greatest velocity. It needs to almost like catch up to the other ones. And red was just taking its time. Red was just like do 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 do. Okay, cool. Now there is a cool demonstration that you could do if you're safe. So instead of all these 3 points on a record in the classroom, I'll have students get in a line and they hold hands or they hold on to like a piece of rope. And the rope, I say, keep the rope nice and straight. And they move around in a circle. So the person at the end, what do you think they're doing? They're like sprinting to try to stay in line with everybody. And the person in the middle is just kind of like do 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 do. So if you could visualize that, but don't do it because without fail somebody almost trips and falls and hurts themselves. So don't hurt yourself. Okay, that's a disclaimer. Don't try that at home. But it's just a nice visual to have in your head of somebody running around the outside of the circle. Okay. One last thing, I always challenge my students, download this app. I don't get any money from it, but there's an app called One More Line, and it's a game, and it says use your knowledge of tangential velocity and uniform circular motion to beat the high score. I just took this screenshot. That's not my high score. I think at one point I got over 200. So try to get over 100, and if you could get over 100, then you'll have a sense of pride and accomplishment. Okay, but if you want, because it's a cool demonstration of especially tangential velocity. So if you download that game, you'll know what I mean. And that's about it. Thanks for watching, and have a great day.